We're surrounded by concrete. It is literally the foundation of our entire world. But what if I told you that every single time it hardens, there's a secret, microscopic event taking place, a tiny, hidden shrinkage that has massive implications for everything from our homes to our tallest skyscrapers? Well, today, we're going to uncover that secret.
So let's just start with a really basic question. Picture this. You've got that gray cement powder, you add water, it turns into a paste, and then, a few hours later, it's solid rock. Now, what does your gut tell you happened to its size? Did it get bigger? Maybe stay the same?
Well, here is the twist. The final hardened product actually takes up less space than the original stuff you mixed together. It shrinks. And this one tiny, counterintuitive fact is the absolute key to engineering stronger, more durable concrete.
But how is that even possible, right? How can something shrink as it's getting stronger? To get our heads around that, we need to zoom way, way in and take a look at the chemistry of what's going on in that mix.
This right here really gets to the heart of it. On the left, you've got your starting ingredients, the cement and the water. And on the right, you have the final product. Just look at it. The total volume on the right is smaller. And that's because the chemical reaction that happens creates new compounds that are just, well, they're more compact than what we started with. Here's a fun way to think about it. Imagine a big, fluffy bag of unpopped popcorn kernels and a glass of water sitting next to it. Now, if you could magically fuse them into one solid, dense block, that new block would be way smaller than the fluffy bag and the glass of water were side by side. It's a really similar idea with cement. The chemical reaction just rearranges all the atoms into a tighter, more efficient structure. And of course, there's a name for this: chemical shrinkage. It's that reduction in volume that happens simply because the new chemical compounds are denser than the original cement and water. And let's be super clear, this has nothing to do with drying out. This is a fundamental part of the chemical change from a liquid into a solid.
So what does this shrinkage actually do inside the concrete? Well, as it hardens and shrinks from the inside, it creates a kind of vacuum. This vacuum tries to pull in any available water. But if there isn't enough water around to fill those tiny gaps, you're left with millions of microscopic empty spaces, or pores. So this internal network of pores is a direct result of that chemical shrinkage.
All right, this all makes sense in theory, but it kind of begs a pretty big question. If all of this is happening on a microscopic level, deep inside a solid block of concrete, how on earth do scientists actually measure it? How do you see the invisible? Well, the method is surprisingly clever. Remember that internal vacuum we just talked about? The hardening cement will literally suck in water from its surroundings to fill those newly created pores. So, if you can measure how much water gets pulled into a sample over time, you can track the rate of chemical shrinkage. It's that elegant.
And there are two main ways scientists do this in the lab: dilatometry and gravimetry. Now, I know they sound complicated, but the ideas behind them are actually pretty straightforward.
So, first up is dilatometry. You take a sample of wet cement, pop it in a vial, and then you top it off with some water. Then you stick in this narrow, marked tube, kind of like a pipette. As the cement hardens and shrinks, it sucks water out of that tube, and you can literally just watch and measure the drop in the water level. It's a surprisingly simple and direct way to see what's going on.
Gravimetry is just as clever, but it takes a totally different approach. Here, a sealed sample of the cement paste is submerged in a liquid and hung from a super-sensitive scale. As the cement inside shrinks and pulls in the surrounding water, the sample's total mass goes up. The scale records this weight gain, giving you a super precise measurement of the chemical shrinkage.
Now, it is absolutely crucial to make a distinction here. The chemical shrinkage we've been talking about is not the same thing as the drying shrinkage you see when a concrete patio cracks in the sun. That's caused by water evaporating into the air. Chemical shrinkage is an internal process that happens even if the concrete is kept completely submerged in water. Okay, so scientists can measure this microscopic shrinkage, but why bother? What's the real-world payoff? Well, this is where this tiny, nerdy detail has a huge impact on the world all around us. Measuring chemical shrinkage is kind of like having a speedometer for the cement hardening reaction. For example, we know the reaction speeds up at higher temperatures. By tracking that shrinkage, engineers can predict exactly how quickly a concrete mix will set and gain strength in any climate you can imagine, from a scorching hot desert to a freezing cold winter. And these temperature experiments allow scientists to calculate something called the apparent activation energy. Just think of it as a magic number that tells you exactly how sensitive the reaction is to temperature.
For typical cement, it's around 50 to 60 kilojoules per mole. And this number? It's a total game changer for engineers. It lets them create computer models that predict how concrete will behave at any temperature.
And this is where it gets really cool. This graph shows the measured shrinkage for two different types of cement, and then a blend of the two. The dotted line you see is the predicted shrinkage for that blend, based on the other two measurements. And would you look at that? The prediction is absolutely spot on.
It's just like the researcher Dale P. Bentz said. The shrinkage of these blended systems can be accurately predicted using a law of mixtures. What this means is that engineers don't have to guess anymore. They can measure the individual components, do the math, and then engineer a final product with precisely the properties they need.
So in the end, what does this all boil down to? Well, understanding and measuring chemical shrinkage gives us amazing quality control. It lets us predict how concrete will behave, and it gives us the power to design custom blends for any situation imaginable. It all adds up to one thing: safer, stronger, and much more durable infrastructure for all of us.
And that leaves us with a pretty fascinating thought. We tend to think of concrete as this simple, brute force material, right? But as we've just seen, it can be engineered with incredible precision. So if we can fine-tune the most common building material on Earth at the chemical level, what other kinds of smart materials are out there just waiting for us to discover them? What will the buildings and bridges of the future really be made of?